Okay, in 5.1, we talked about the letter E, the number E, and said it was approximately 2.72. It is more accurately 2.712818284845 So yeah, approximately 2.72. That's good enough. And we also, something interesting about E cannot be the root of a polynomial equation that has integer coefficients. So if we have any polynomial equation like ax cubed plus bx squared plus cx plus d, anything to any index, and you factored this out, you cannot get the value e. It cannot be, that's if a, b, and c are integers. We also noted that there's an interesting property that y equals e to the power of x is its own derivative. That also means that it is its own higher derivative, so you could integrate or perform integration on this, which would be derivation backwards, and you'd always get y equals e to the power of x. At any rate, we can discover that by throwing it into Desmos and graphing it, and then graphing its derivative. But in this lesson, we've already affirmed that it is its own derivative. In this lesson, we want to learn about its inverse function, which is the natural logarithm. And we're going to do that just by drawing it. I'm going to kind of sketch it out. We already know that if we have the function y equals e to the power of x, the inverse of that function, the inverse of an exponential function, is a log function with the same base. So the inverse is the log, I'll use y equals the log of x base e. Now, because the number e is used so often in real-world applications, and because it's a special value and all of those things, it actually has its own special log. So this is the log of x, the log of x base e, is actually denoted as the natural log of x. And so the natural log is a log with a base of e. That's all it is. And if we sketch this thing out, we can see what it looks like with a couple of key points. I'll sketch y equals e to the power of x, which would look something like this. It probably grows a bit faster if I... Okay, this is y equals e to the power of x. It has key points like 0, 1, because anything to the exponent of 0 is 1. It also has, if x is 1, then we'd be going through e. So there's some key points on y equals e to the power of x. And then if we take its inverse simply by reflecting it over the line y equals x, we end up with a logarithmic function that looks like this. And this is the function ln x, or the natural log of x, pronounced ln x. Its key points that it goes through, instead of 0, 1, will be 1, 0, and instead of 1e, it will be e1. So this is a graph of the natural log of x. It is just log of x base e. You can graph any log. You would put the common log is, if we don't write anything like log x, that's the common log, which is log x with a base of 10. So that one's special. It's called the common log. And now we have another one with the base e, is called the natural log. And again, you could take the log of any base, okay, And yeah, the log with a base of e is just, it's just a value. It's just a special value, and it gets denoted natural log of x. Other key characteristics of the natural log of x are very similar to the log of x, any other log with any other base. The domain and range from the exponential graph and the logarithmic graph are flipped. And this one has, our pink graph here, the natural log of x, has no y-intercept. It has a domain restricted to values of x greater than 0, and has a vertical asymptote at x equals 0. There's no point of inflection. Its slope is always positive, but it's positive and decreasing, whereas the exponential graph is positive and increasing, but there is no point of inflection. It's never going to turn and go down or flip and go back up. And it's mostly what we need to know about the natural log of x. You can calculate things using e the same way as you would with other values. Your calculator is really helpful there. So if we look at example 2 for lesson 5.2, we're just evaluating expressions using e. So in A, we have e to the power of 3. And we would just put that in our calculator. A scientific calculator has an e button, might be a second function button. You raise it to the power of 3, and we get that e to the power of 3 is approximately 20.086. Our second one there, we have e to the power of -1/2. Again, you could put that in your calculator. You might need to rewrite it as e to the power of -0.5. That might be easier. And that is approximately 0.607. If we're looking over at example 3, so here we were dealing with exponential functions involving a base of e. Now we're going to be looking at evaluating log functions with a base of e, which is the natural log of x. So the first one that we're looking at is taking the natural log of 10. Now in your calculator, again, you have a natural log button. It's probably a second function button, but you can just type that and that will be, you don't have to write this, but this is what it's doing. It's going to take the log of 10 base e. Now if you did the log of 10, the common log of 10, you'd have the log of 10 base 10, which would just be 1. Okay, this is not going to be that. This is going to be different. It's going to be the exponent that you need to raise e to get 10 if we were going to convert it into exponent form. You don't have to do that. You're just going to chuck it into your calculator as is, and you're going to find out that that's approximately 2.3. So again, just as a reminder, what does that mean? That means that e to the power of 2.3 is approximately 10. B, we are told to evaluate the natural log of -5. And we need to remember that this is undefined. Undefined. You cannot take the log of a negative number. Just like you can't take a common log of a negative number, you cannot take the natural log of a negative number because the domain of logarithmic functions is restricted to positive values of x. Example 3c says take the natural log of e. Well, that one's actually really easy. Just like we said up here, the common log of 10 is 1. If the base is the same as the log that you're getting, that you're hoping to find out, this natural log has a base of e. So a log e with base e is 1. And one other note, a property that we can use, it's the same as any working with any log, but something that's helpful when we're solving equations involving exponential and logarithmic functions, especially when we're trying to get exact values and avoid the use of the calculator until we absolutely need to. But it states, note, the natural log of e to the power of x equals x. So that makes sense. It's saying that x is the exponent that we need to raise e to get e to the power of x, right? Because this would be a log base e. So e to the power of x is e to the power of x. That's easy. What else? E to the power of the natural log of x equals x. This is essentially the same statement, just now it's in exponential form, whereas here it was in logarithmic form or natural log form. So here in exponential form, we are saying that the natural log with a base of e, so log base e, log of x base e, we're going to take e and raise it to that power, then the answer is going to be x. This one makes sense if we rewrite this in log form, then this says that the exponent right here is equal to the log of our base, the log of x, and with a base of e. I'm saying that wrong. But if you convert this into logarithmic form, you get this statement, which is true because the natural log of x is the log of x base e. In example 4, we have bacterial growth. We have a population of bacterial culture as a function of time is given by the equation p with respect to t is 200 times e to the power of 0.94 t, where p is the population after t days. So we're given an initial population of 200, if we're familiar with our exponential equations. We're given a growth factor of e, which is approximately 2.72. And we're given this growth expression, growth function, in terms of t, in terms of the time it takes for something to grow. But we could also communicate population growth. Another way to communicate population growth, and we'll see at the end of this example, is with a doubling period. So here we have an exponent of e. A doubling period would have an exponent of 2. And then you'd have it in terms of doubling periods, and we would have to figure out what this exponent is. It would be the number of doubling periods involved or allowed to pass. At any rate, in this one, we have in terms of days, and we can say it's going to take a lot of days before you get one full growth period by a factor of e. So because every time we put in a day, 1, 2, 3, 4, whatever that value is, we're going to be multiplying it by 0.094. So it's going to take a bunch of days before we get actually 200 times e to the power of 1. At any rate, we don't have to do that right now. Instead, in A, we have to determine the initial population. Initial population, we can do that at any time by setting t equal to 0. If we set t equal to 0, you'd get an exponent of 0. E to the power of 0 is 1. 1 times 200 is 200. But if we know how our exponential equations work, then we know that the initial population is just given. Initial population is 200. B says estimate the population after 3 days. So we need to set t equal to 3 and then just sub that into our population function. Sub t equals 3 in. We get 200 times e to the power of 0.094 times 3. We can simplify our exponent. We get 200 times e to the power of 0.282. E to the power of 0.282 is 1.3257, etc. You can just save that in your calculator and then hit times 200 times answer, or just times 200, and we will get approximately 265. So the number of bacteria after 3 days is approximately 265. The bacteria culture will have a population of approximately 265 after 3 days. Now, in C, we're asked how long will the bacterial culture take to double its population? How long to double? So this is getting us an answer to a question, how long will it take to double, but that's also going to give us our doubling period, which is going to help us in D, which says to rewrite the function as an exponential function with a base of 2 instead of a base of e. So how long will it take to double? All we need to do is determine that our initial population is 200. So to double, we're going to put 400 in for our population. Divide both sides by 200. .094t. And now we can take the natural log of both sides, which looks like this. Take the natural log on the left of 2, and over here the natural log of e to the power of 0.094t. And then because the natural log has a base of e, we know that the natural log of, what did we do? Since the base of the natural log is just a log of e base e, we're really asking on this right side, what exponent do we need to raise e to, the base of the natural log function? What exponent do we need to raise e to in order to get e to the power of 0.094t? Well, the exponent that you need to raise e to get this is simply the exponent here. So on the right side, you reduce it to its exponent, 0.094t. On the left side, we have the natural log of 2. And now I can divide both sides by 0.094. So t equals the natural log of 2 over 0.094. Which tells us that t is approximately 7.4. So that's in days. That's how long it will take the bacteria culture to double, which now also then gives us our doubling period. So when we move over to D, and we have to express our population function with a base of 2, we know that the number of days is going to be divided by our doubling period, which is 7.4. So again, this, to clarify why we have a fraction here, this is the number of doubling periods expressed in terms of days. So for example, if you waited 1 week, you'd sub 7 in there. You'd get very close to one doubling period. This will be very close to doubling after 7 days. If you did 15 days, it would double twice. You'd have 15 over 7.4, which is about 2. So it would have 2 factors of 2. It would be 4 times this would be 800. So it would double twice. Again, this is the doubling number of doubling periods expressed in terms of days, which means you need to take the number of days that you're wondering about and divide it by 7.4 to give you the number of doubling periods. Okay, a couple of final notes for this one. Just as a reminder, we have that the natural log of x is equal to the log of x base e. We have the natural log of x is the inverse of e to the power of x. And just the concept that this letter e, the number e, and the natural log of x, log base e, x, is used in a lot of real-world applications.